Okay, hello everyone. So this is going to be a little bit basic, but simultaneously go over the important parts for looking at conjugate heat transfer. So modeling a solid and the fluid simultaneously as discrete elements in STAR-CCM+. So we'll keep this basic and generate everything inside of STAR-CCM for this one. You can absolutely do all these same steps after the generation of the geometry with geometry that you've imported from exterior sources of some form. So we'll keep this simple for starters, and what we'll do is we will look at a combination of, we'll look at a couple different types of things, but effectively natural convection and forced convection over a sphere in a vertical column of air. So first things first, let's put our sphere in. Let's create a sphere. This sphere, we'll have the sphere centered at the origin. That seems to be a fine idea. We'll give the sphere a radius of 5 centimeters. So that's going to be a diameter of 4 inches. Not the biggest sphere in the world, but fair size. So click OK. If we open up a geometry scene, we should be able to see our sphere. It's a sphere, nothing to look at yet. Nothing much to look at yet, at least. So we're going to create a cylinder as a vertical column of air. The start coordinate, we're going to go with, let's say we're going to start this below -2 meters below our sphere, and we're going to extend 2 meters above it. So we're actually looking at this thing upside down. Oh, wait. No, I'm looking at this incorrectly. If we're doing this two-dimensionally, we need to do this in another axis. If we're doing this two-dimensionally, this needs to start, z equals 0 is fine. This needs to start at -2 and go to 2 in the y direction. Because this will be two-dimensional because we want to keep it relatively easy. We do not need it to be this large. We want it to only be about 15 centimeters in radius. So like air can get around this thing, but it's simultaneously not the easiest for air to get around it. So this will be like a tube that you're either forcing or letting air naturally convect through. Great. Okay, so now what we're also going to do is we need a plane. For the two-dimensional purposes, we need to cut all of these in half. So we're going to create a big block. I'm not terribly concerned about the exact dimensions here. We're going to make sure this block encompasses everything. So this block wants to start at, let's go with -0.2 to 0.2. So it's wider than our cylinder. It extends from -3 to 3, and one of its corners must be on exactly z equals 0. So hit create there. So we have 3 things. And actually, I'm just going to nuke this geometry scene and create a new one so we can see what's up. Geometry. So we have a block that is cutting off half of our cylinder, and inside of the cylinder is embedded our sphere. For the cylinder itself, the surface, before we start doing any funky operations to make our domain, we're going to break it into 3 sections. So we have a top, bottom, and side surface. We will name them as such. I'm placing and calling the top, the side at positive y. Theoretically, you can do this any which way you want. You just got to be careful to reference which one is top and bottom and make sure gravity matches it. For the purposes of natural convection where gravity matters. Realistically, splitting the block surface shouldn't matter too much, but we will split it anyways. Because one of these planes is going to be our simulation plane. So I'm just going to name this plane. The rest of these surfaces should be irrelevant on the block, and the sphere only has one surface, which is conveniently already called sphere, but we will just change that to sphere. So, a couple things here. We will do a Boolean subtract. We will subtract everything away from the cylinder. And this is going to give us our air domain. Well, actually, I'm feeling like what I probably want to do is modify the size of this block a little bit. So we had some specific sizes, so we will go ahead and make everything the exact correct size. I was making it oversized as a bit of a precaution, but I'm starting to think that's going to mess up more than it's going to help fix. That's curious. Although I guess this is 2D, so it doesn't need to be a cylinder. The cylinder is if I wanted to do this 3D. If I want to do this 2D, theoretically, it doesn't matter. Oh, okay, let's take a look at this again. This is a little bit curious why this subtract doesn't quite seem to be doing what I think it should. Although at the same time, it appears to have done what I think it should. So it is a little bit curious. Yeah, that thing is doing what it should. Okie doke. So it does indeed look like we have our air domain, but we also need to subtract off half of our cylinder, or half of our sphere, excuse me, because we also need a solid. So we're going to do another subtract operation. This is going to cut off. We're going to call this a domain subtract. We're going to call this a solid subtract. We're going to call this solid. Okay. So this should have effectively. Can I reset the view here? Geometry seems to be just a little bit broken on me. There we go. Yeah, so we have the walls of our sphere, we have the plane of our sphere. So we have everything we want. So this will let us simulate both a solid and the air around it. So we need to create a mesh for both of these. We also need to put both of these in a region. So we're going to, oh, actually, first things first, we need to make sure that these are noted as contacting. So this is realistically easiest to do probably at the highest level. We want to tell this, hey, this surface of, or so we have the air, we have the surface of the sphere here, and we have our solid down here. We want to say that these two are touching. Notice that if I select both of them, they show up as two names. You can kind of see them on top of each other there. They're in the same place. They are the same surface. So we can say create weak in-place contact. Or alternatively, I think what we can also do here is create a new operation for, let's see here. Where I believe it's imprint is what it will do. And this will let us make it detect contacts. Notice that a contact appeared here when I said imprint. So what imprint does, let me back up a second, is that it says, hey, take a look at whatever surfaces, whatever parts. In this case, I selected the air and the solid. And find out where they are touching. Where they are touching, make them a different part. Make them a different surface. Should be very precise about my nomenclature here. Make where these parts are touching a different surface, and make where those parts are touching a contact. So very, very specifically, it made a contact between our solid sphere right here and the same surface on the air side. And we, without actually manually creating one, it had created a contact right here. So this is important. You need to make sure there exists a contact that highlights all of the surfaces where you expect your parts to be touching. Where the air or fluid in general touches the solid, where you want them to interact, there must be a contact there. That way, we go here and say, assign parts to regions, create a region for each part. So we'll have two regions, one for the solid, one for the air. We also create a boundary for each part's surface. And by default, it says create boundary mode interfaces from contacts. That's what we want by default. So we click apply, and we go look down on regions. We can see that we have two regions. We have one for solid, one for air, both with several boundaries. Also, very importantly, we can see that there's an interface that showed up here. And there's an interface that showed up here. It is detecting that these are where these are touching. Because there existed a contact, when we created the region, it created an interface. The interface is what lets these two regions communicate the physical information between them. If there is no interface, they are not interacting according to the physics. Now, we do want this to be 2D. We could let this be three-dimensional, but for the sake of time, we don't want it to be three-dimensional. So I'm going to badge both of these for 3D meshing. And actually, because I created these regions first, I need to delete these regions, which also got rid of that interface, incidentally. And we're going to assign parts to regions again. Note that there does not exist a Control-Z option in STAR-CCM+. That is not a thing. Now, theoretically, this should be two-dimensional. I'm having a hard time seeing. I mean, it definitely does look like it's fully 2D, so we should be okay. Because we do see this little red. It's probably hard to see, but there's a little red dot next to solid, a little red dot next to air. That means those are two-dimensional parts. And they both showed up here. We do have our interface. So we should be able to create continua now. So the first one we're going to create is for air. It is two-dimensional. We're going to say it's steady. In practice, the flow around spheres is highly non-steady. But we're going to pretend like it's steady for these purposes. We're going to be looking at air, so it's a gas. Segregated flow. This does want to be an ideal gas flow with segregated fluid temperature. Turbulent, and we'll go with K omega for this one. Now, I do want to note is you don't necessarily need the air to be ideal gas. I'm going to switch it back to ideal gas in a second here, but if you select constant density, there's a optional model called the Boussinesq approximation or Boussinesq model. This will, without actually changing the density of the flow, effectively act like, for the purposes of gravity, that you are changing the density of the flow. So you can model natural convection with a constant density model if you wish, but it is an approximation rather than a more accurate model of changing densities. And because we do want to model natural convection, we do need gravity. We do need to know that gravity is a thing here. So we're going to rename this as air. All the properties it have picked for gas by default are going to be the properties of air. So this is all fine. But we need to tell it a couple of things here. We need to make sure gravity is going in the right direction. This is important. If gravity is pointed the other way or pointed in a direction you don't expect, things can go sideways, literally, in ways you don't expect. So gravity is a reference value. I should really turn that down a little bit. Gravity is a reference value. There we go. Gravity is a reference value. In this case, it's pointed in the negative y direction, which is what we want. Gravity will be pointed down. The flow will have a tendency to rise up. The rest of this is fairly, well, actually, this one is actually very important. The reference density needs to match the density of really your inlet boundary condition. This should be your far field condition right here. So I'm going to say this is going to be pretty darn close to 1.18 kilograms per cubic meter. By default, it's 1, which is a problem. Because realistically, that's significantly lower than most densities until you get the air really hot at sea level. So you need to change your reference density. If you don't, you'll wind up with weird effects, like the simulation will swear up and down that hot air falls. And if you don't change this value, it'll be right. Sort of. So change your reference density. Make sure it matches whatever the free stream value is for your simulation. For the purposes of this case, that will be about 1.18 kilograms per cubic meter. You should make that match as closely as possible. Initial conditions, we can just leave it 0. It'll figure out what's going on. So this is our air. Well, actually, yeah, this will be fine. Now we need to create a, not a mesh continuum. Sorry, that's not what I wanted. Delete all. I accidentally deleted the regions. Let me create these again. So when I said yes to, am I sure I want to delete the mesh node I accidentally made, it deleted the air and the air and the solid regions because those were dependent upon the mesh node that I had just accidentally made. So we want to create the physics for our solid model now. It's still two-dimensional, still steady. This is going to be a solid. And segregated solid energy, constant density. So the density of the solid is not going to change, but it will track the energy and the temperature of the solid. By default, it's going to assume this thing is aluminum. Let's just go ahead and update that. Let's pick some other material. So instead of aluminum, we want this to be a 4 centimeter, I think it's a 5 centimeter radius sphere, so it's about a 4-inch diameter sphere of, let's see here. I'm thinking stainless steel if we can find it. Yeah, there we go. Stainless steel. It's going to be a particularly heavy sphere. Click OK. Oh, actually, hold on. Replace with. It did not take that for some reason. There we go. Now it took that. Stainless steel. So this thing is going to be heavy. This is going to have a density of about 8,000 kilograms per cubic meter. This little sphere is going to have quite a bit of mass to it. It's not nearly a cubic meter, but it's still going to be a fair bit of mass. So this is our solid physics. And we told it it's a solid. We told it it's 2D. We told it that it's steady. We told it that the solid is constant density and to track via segregated solid energy the temperature of the solid. So right now, both of these regions have this little blue symbol. If we look under physics continuum, they both are called the air physics region. We need to change the solid to use the solid physics continuum. Sorry, not physics region. They were both using the air physics continuum. We need the solid to use the solid physics continuum. And notice the symbol changed from blue to gray / brown / black, whatever, to indicate that this is solid. That's important. That tells you that it is using a different solid physics continuum. And you see that this interface shows up as a contact interface. It is interpreting these as touching now because it knows one side is a liquid, fluid, one side is a solid. Now, what we're going to do here is we are going to say that this solid region is heating up. So we can do that with a physics condition. We can say the sphere, the solid, is an energy source. Now, this is going to get a little bit confusing because in truth, because this is a two-dimensional simulation, this sphere extends effectively a meter into and out of the screen, or into the screen. All right, it has a span of 1 meter because this is a two-dimensional simulation. So what might be easier is to say that this has a specific heat source or a volumetric heat source. This generates some amount of heat per unit volume. So if you had a 4-inch diameter sphere, that's... well, let's do some mental math here. Oh, actually, we can do better than this. We don't need to do mental math. We can write an expression. So if we click on the little ellipses here, we get a little bit more definition. We can change the definition. We can change the units. We're going to click on definition, and it opens up this box to modify values. We're just going to do math here because we can, and I don't know what number I want to use offhand. So a 5-centimeter diameter sphere is going to have a volume of, I believe, 4/3 pi r cubed. Times 0.05 raised to the 3rd power. So this is the volume. So if we want to add, let's say, $50, we can divide. I believe this would take units. Let's find out. No, I didn't like my units. Okay, well, we're using base SI units, so theoretically we shouldn't need to tell it what units we're using. So if we want this to generate 50 watts total, we say 50 watts, 50, divided by the volume of the sphere. Click OK, and it evaluated this to some value. It should have. Wait, why did it not? Oh, maybe it doesn't like the power symbol. It might be picky about this. This might need to be... Yeah, I think we need to use the power function. 0.05, comma 3. Let's try putting my units back in and see if it likes that or not. Nope, it still didn't like that. It seemed to have taken this, though, although I'm not sure if it evaluated it or not. No, it seems to have taken it, and that should be conceptually right. So we're looking at 50 watts per this entire sphere divided by the radius of the sphere. Now, again, this is going to act 2D, so this isn't actually a sphere. We're sort of hand-waving that part away. If you wanted to truly make this act like a sphere, we would cut this down the middle and make it axisymmetric. So the last thing we should really need is to set up our boundary conditions. So these cylinder walls are indeed going to be walls, so flow can't move through them. The sphere is an interface. The top is going to be so we'll do natural convection first. So we're going to make the top and bottom. We expect the bottom to be a stagnation inlet. So what I'm going to do here is say basically everything is stagnant. Like this is just natural flow coming in through here. The top is a pressure outlet. It'll just be 0 Pascal flow leaving through the top. If any flow comes in through the top, it will come in at 300 Kelvin and 0 pascals. I think that should be enough to actually simulate things. Let's find out if I'm correct about that or not. So let's select. Let's look at temperature and see how temperature changes here. So for the moment, oh, we skipped a very important step, which is the volume mesh. Let's fix that. So we need to mesh these guys. So new mesh, automated mesh 2D. We're going to do these one at a time. We're going to use a poly prism layer mesher for the air. We'll also separately use a poly mesh for the solid itself. So this is a relatively small sphere, so I'm going to go with a 0.5 centimeter base size. Target is 100%, minimum is 12.5. The rest of the, we'll go with 5, just to make sure that there should be more than enough cells in here, but I'm making this surface proximity minimum 5 just to be safe. Prism layer is going to be pretty important for thermal boundary layer, so we're going to crank that up to 12. And 50% is usually a good spot to start with for prism layer total thickness, so I'm going to leave that there. We're going to do a couple things here. We're going to create a new surface control to limit max size on our simulation plane. And to do that, we are going to change the target surface size from parent values to custom value to, I'm going to say 1600% to start with. Oh, I said 0.05 centimeters. Whoops. That should be 0.05. That should be 0.5 centimeters. I accidentally knocked off an order of magnitude. That would not have been pretty. New surface control. We also want the walls and the far field to potentially have coarser cells. They can be smaller, but they can also be coarser. So we're going to just up the target size here also to 1600%. And we're going to mesh that and see how that looks. Yeah, okay, this probably needs to be more like 400, if I had to guess. And that base size can come down. We're going to go with 1/8 of a centimeter instead of 1/2. And now we can probably make that max size bigger again. Let's go back to, well, we'll go with 1200. We'll split the difference. Because theoretically the flow is sealed in here. We will actually get a boundary layer on the sides here. It won't actually be a very big boundary layer, but or a very, it won't be a very important boundary layer, but it will be a present boundary layer. So let's go ahead and modify some of these properties here. We'll make that boundary layer considerably thicker, and we'll give it like 6 layers instead. So this is changing the boundary layer out here only on the walls primarily. And realistically, this looks like it needs to be much thicker than that. There we go. That's better. So we should get a pretty high definition boundary layer down here. We have a lower definition boundary layer out by the walls. And then flow should proceed all the way up and through this thing. I'm just going to knock this down. We'll leave this with 800, I think, is probably reasonable. How many cells do we got? This is only like 32,000 cells. This is a lightweight simulation. This should be fine. But we still need to mesh the solid. So we're going to do a new automated mesh 2D of our solid. We're going to do a polygonal mesher, but we do not need a prism layer. Solids do not have boundary layers. Name this. So this just needs to be a polygonal mesh. And that means the base size can be fairly straightforward. Oh, that is one thing I forgot to change, though. I forgot to modify the surface growth rate. This wants to be slower. We'll make that change effective in a second here. So 0.125 centimeters. And we'll just mesh and see what it looks like. Let's go ahead and add to our mesh scene. We want to know not just what does the air look like, but also what does the solid look like. So let me click OK there. And this is what our solid looks like, which is pretty good out here by the wall, but it grows a little bit quickly. So I think we can get away with just turning down in our solid mesh, if I can find where that went. Turn down our surface growth rate to, 5% is kind of my go-to. There we go. That looks much better. So it's very, very close. These are basically the same mesh at this boundary. That's actually kind of important. You want the mesh across an interface to look as close to exactly matching as you can reasonably get it. This is really good. And then it can diverge a little bit further away. So now if we hit run, it should run for starters. And we're not looking at anything. Oh, because there's no parts under our scalars. There we go. So this thing is heating up. You can see the temperature of the sphere. It's non-uniform. Extremely non-uniform. We have a lower temperature, well, in the surface, obviously. You can actually see the boundary layer here. There's a lower temperature on the facing side and a higher temperature on the leeward side of the cylinder. And you can see it getting into this cyclical back and forth oscillation, characteristic of vortex shedding off the back of the cylinder. So one thing that I'd like to show you briefly, this is effectively a natural convection simulation. This is what's going on here. So we can, well, for starters, let me kill that stopping criteria so it stops stopping my simulation. Let this keep on running. The other thing we can do is instead of adding heat everywhere, a volumetric heat source to the entire solid. So I'm going to stop this for a second here. And we're going to set this volumetric heat source to 0. So it's going to stop generating heat. This thing's going to start to cool down. Notice the high point of this is dropping quite rapidly. Well, reasonably rapidly. So that's cooling down, which is fine. we can also add heat directly to an interface. So right where this fluid touches, we can say that we want to add heat as an energy source, as well, this is also weird. So realistically, if this is like a circumference, we can also do a heat flux. And we can say, let's add just like 10 watts to that boundary. So 10 divided by 2 times pi times r. Yeah, just 2 pi r. That's just the circumference right there. And then 1 is the other dimension. So yeah, this should be fine. So this should add 10 watts per, well, just 10 watts. It should add 10 watts over the circumference of this thing. See if we can notice that. It's going to be pretty subtle. Let's crank up the heat flux. We'll make it something obvious so we can hopefully see that it's adding a lot of heat. Okay, why doesn't this want to actually look like it's doing anything? Oh, there we go. It's definitely adding heat now. It just took a lot. There we go. You can actually see that there's a thermal gradient coming in from the surface. It's heating up fast now. Now let me not dump 10 kilowatts into a sphere the size of my fist. That sounds like a recipe for melting something. Notice that at this particular flow configuration, the flow actually isn't very unstable behind this thing. It's actually pretty stable due to the thermal boundary conditions and the strong natural convection from going from 600 Kelvin down to 300. But let's visualize what this flow looks like a little bit in terms of how it moves. So let's make a vector scene. And with this vector scene, well, we can see a whole bunch of vectors that look like something not very intelligent. So let's change this vector scene from glyph to line integral convolution, for starters. We can see our velocity field, which makes absolute sense. We have kind of a boundary layer in the wall. It goes around the sphere, which compresses that boundary layer in the wall, and then it kind of spreads back out, and we have this turbulent effect run back up our tunnel, for lack of a better term. But let's simultaneously look at where the flow is going and also look at the temperature. So we can change this color mode from the default vector magnitude, which colors it based on the magnitude of the vectors, to look at whatever the heck we want. So instead of looking at velocity, we can look at temperature, but still see where the flow is going, which does also, incidentally, a beautiful job of highlighting the difference between the solid and the fluid, because the fluid is moving, the solid is not. So this fluid has this line integral convolution hash lines to tell you where it's going. The solid has no lines, so we can see very clearly the divide between solid and fluid. We can see the thermal boundary layer, especially as that grows. If we wanted to, we can probably turn on, where is it? I'll tell you what. What I'm going to do is we are going to just select everything and show the mesh. So we can see what the mesh looks like. We can see what the flow looks like. So one thing that might be useful here is we might actually want to refine the flow behind the cylinder. We can kind of see that this wake starts to dissipate really quickly. Part of that is just because the mesh gets really coarse up here. So let's try and fix this. Let's add a... Let me stop iterating for a second. Let's add a surface control wake refinement. Surface control wake refinement on our sphere. And this is going to sweep wake refinement. This is going to sweep in the positive y direction, so 0, 1, 0. It's going to sweep for, let's say, 1 meter. We're going to give it a really small half angle. We're going to give it like a 1.5 degree half angle. We basically just don't want the cells growing too much, so we're going to set a 200% size and the growth rate of 1.05, so 5% growth rate. And let's remesh. So we should see a large section of this get a lot smaller. Yep. So we have a large section of this running significantly downstream that got a lot smaller all of a sudden. And yes, it runs slower because there's significantly more cells now. But this wake should have significantly more definition as it fits pretty much entirely within that refined region. And notice that it dissipates much more slowly. So if I turn off that mesh scene, wait, hold up. There we go. If I turn off that mesh scene, we can see that this wake actually propagates pretty far upstream, visibly. You can see the flow pattern have this kind of oscillatory behavior. So that is one way to do this, but we want to look at a couple of things here. Like, what values do we care about where these are interacting? So I'm going to stop iterating here. And actually, I'm going to completely clear the solution. So we're going to start from no solution. And let's take a look at several values here. So let's look at the minimum and maximum. So this is sort of validation for, like, is this flow working properly? So let's see here. Rename. There we go. So we want to look for the minimum and maximum surface pressure coefficient on the surface. Well, the thing that has pressure is the fluid, so you want to make sure to select this on the air side. Most of these values we're looking for on the air side, realistically. We want to know also how much heat transfer is moving through that surface. So you can select either side of the interface. The important thing is this adheres to the vector math for heat and fluid flow. Heat moving into the domain is negative. Should be. We have no data at the moment. But heat flowing into the domain, I'm very certain is negative. Heat flowing out will be positive. So we can also say this is the heat transfer sphere. Oh, crap. I completely forgot to check something. I will do that in a second. Rename. We can track the heat transfer, not just where the solid touches the fluid, but we can track it everywhere. We can track how much flow enters the domain. We can track how much heat exits the domain. And we can track them on more than one surface. So we can say heat transfer, and we can say, I want to know all of the heat moving through all of these. And theoretically, the answer should be 0. The answer should be net 0. Because this is a steady state simulation. We also might want to look at, this would be a system, no, this would be a metric. The surface average heat transfer coefficient. Now, with some coefficients, especially field function coefficients, you need to be careful. Because they have typically defined constants that you need to worry about. So for our purposes, heat transfer coefficient has a reference temperature of 300 Kelvin. So that's fine. But if your reference air temperature was anything else other than 300, you would have to update the value down here, or this would make absolutely no sense. And there are multiple ways of measuring heat transfer coefficient. So let's take a look at some of that for the moment, and then we'll hopefully see how that works. So let's go ahead and create a monitor and plot from these. We'll create a monitor and a plot from these. And of course, max and min temperatures is something you can want to plot. I'm not literally plotting everything for this one. Just some examples of characteristic type things that might be interesting. So you can see that in this case, a lot of heat is coming in with the flow. A lot of heat is leaving with the flow. And the difference theoretically should be something. Actually, I think I turned that off, didn't I? Hold on a second. The difference is only like 10 watts, maybe. So, yeah, the difference is only like 10 watts. So let's crank this up to something much larger. And you can see that this is kind of stabilizing at a vaguely value that's somewhere in that neighborhood. But let's crank this up to 5,000 watts. And we can see that suddenly a lot of flow is coming, or a lot of heat is coming in through that sphere surface. And as more heat makes out through the sphere, this net is actually working its way towards 0. It's going to do it pretty slowly, but it is working its way towards 0. Let's go back and look at temperatures really quickly here, or pretty much anything really. Yeah, so this is such a strong temperature gradient that the flow is actually not quite attached to the cylinder, but it's following in a nicely developed flow field that's driven by natural convection. And the air temperature does get up to quite high values, honestly. So let's look at we can also look at the mass flow average temperature. Create a copy of that. Copy, paste. So mass flow average temperature in and out. Oh, sorry. Mass flow averaged, not mass averaged. There we go. So we're going to look at the inlet. And let's see here. This is going to be the outlet. So the top. So one thing to note about solids is that they typically take a long time to converge thermally. There is a trick that can help expedite this, and that is by changing this under relaxation factor. So under solvers, under segregated energy, you can change the solid under relaxation factor and potentially the fluid under relaxation factor to be higher by about an order of magnitude, asymptotically to 1. And this will help, assuming your simulation is reasonably stable. If your simulation crashes on you, you might need to back these off. But if your simulation is reasonably stable, you can make these changes and kind of accelerate the convergence of temperature. So notice that this thing's out at, a couple thousand iterations, even post this change. And it is nowhere near converging yet. Like this is very definitively, everything is still moving. We can even look at the residuals and see that they're pretty noisy. Natural convection, you're not going to get these residuals to come down very far because there's no forcing function. But you can indeed notice some amount of stability by looking at temperatures, by looking at the heat transfer, by looking at heat transfer coefficients, which this one is natural convection. It looks like it's about 8 is pretty much what this HTC is converging at. Thereabouts. It's oscillating a little bit, but so we can also look at mostly an entirely different scope of problem by forcing the flow. This is natural convection. The only thing that was moving that flow was the buoyancy differences due to heated air. We can also say, nah, I want to move flow over this at 5 meters per second. Let's take a look at the vector scene. And this is going to look significantly different. So let's also just look at a regular old vector scene. That's not what I wanted. New vector scene. Switch this to line integral convolution. So A, this is a lot more energetic, right? We've got velocities ranging between 5 meters to 11 meters per second. So flow is moving pretty rapidly through here. We've got a particularly chaotic sort of turbulent wake going on here. And if we look at any of these monitors, we see that things are, at least they appear to be loosely converging much more rapidly. Although my graph for heat transfer coefficient kind of appears to have broken. There we go. I got it back. Sometimes resetting the axes, just like locking and unlocking and changing the axis values, is enough. But the big thing is this heat transfer coefficient is much higher. It was like 8 before. Now it's 28 by forcing the flow at, 10 meters per second or whatever. So let's see here. The heat transfer net is, well, definitely not stabilizing at 0 because this is a highly, highly unstable situation here. But we've got our heat transfer in, heat transfer out, the net between the two, or between all of them, actually. And then how much is coming in through that sphere. So it's definitely not stable. You can see oscillations due to the vortex shedding off of the sphere. But the temperatures in general are a lot lower than they were. Like, don't get me wrong, this is still really freaking hot. But we get this temperature gradient that's changing through the sphere. It's like 800 Kelvin instead of like 2000 Kelvin. A whole bunch of things are different. So I need to check something. Where is chat? Okay. So this is certainly one possible way where we just have a solid body. We could also have it where it's not actually a solid body. You could also have a hollow body. So let me go ahead and briefly change a couple things here. For starters, we're going to get rid of this solution. The second thing here is we're going to create a new sphere. So this one's going to have a radius of 0.04 meters. Let's go 0.035. Let's have a little bit more shell thickness than that. Great. So here's what we're going to do. We are going to when we cut that sphere in half, we're actually going to modify this to include both spheres. And in theory, what should change here is that our solid will be hollow. Let's take a look at this real fast. If we look at a mesh scene, should be able to see, yes, our surface is hollow now. So, I think I already cleared the solution, but out of an abundance of caution, let's clear it again. So let's go ahead and take we want to, instead of adding heat to the volume, which we can still do, we can still add heat to the entire volume here. But let's not. Let's go ahead, or sorry, we can also still add heat to the interface. It's not what we want for the moment. Set that to 0. We can also add heat straight to a boundary, although I need to recreate this because it's broken a little bit. So let's assign parts to region. So the issue was, to be clear about why I deleted it and remade it, is one of that when I selected the solid domain here, which this is interesting, it still appears to be wait a second, I'm confused. Sorry, 1 second here. Why do we have multiple solid domains? So we get rid of that, get rid of that. Solid, assign parts to region, 1 region for each part's surface. Boundaries. There we go. Okay, that's better. We didn't have a separate boundary for the inside. We had the outside and the inside, and they were just one surface, which does not work very well. So let's go ahead and make this a solid again and run our mesh operations again. And again, this is running very, very fast because it's 2-dimensional for starters. There we go. It is 2-dimensional and relatively small. You can get much, much larger models than this. But what we can do here is we can add heat to this inside surface. So I can say this inside surface is a heat flux. And I'm just going to borrow the heat flux that I used. Oh no, it got gotten rid of. Okay, never mind. I'm going to rewrite this. So let's say 100 watts per where no, it's 100 watts over the entire thing. So 2 times pi times r. This is the inside radius, so 0.035, and it's just r because this is circumference. And the through depth is just 1, so that should be fine. So if we hit run and look at a scalar scene and add. So because I deleted a region, all of these scenes forgot that there was a solid region. We can add it back. And now we can see some slightly more precise temperature gradients because the heat's added here and it has to flow out through a thin shell wall, relatively thin shell wall. So we get temperature gradients through the wall as a result of this. Also, if you know there should be a temperature gradient, but you can't quite see it, you can increase the number of levels on the color bar and kind of get more gradient visibility. So you can either have a solid body, you can have a relatively thin body that's just a wall thickness. Just don't make this wall thickness too thin, because if you do, you're not going to have enough cells in that boundary. Like, for example, here, I could make this very, very close. Let's say, oh, I'm probably going to regret this. That. And in the mesh scene, well, this only has a couple of cells of thickness to it. So this isn't really very accurate temperature-wise. Can you do it? Yeah, but it's harder to have an appropriate number of cells in it. This is probably too few cells, honestly. If I wanted to make this more accurate, I would need to crank up the surface proximity to number to probably more like 5 or 6. Which, on one hand, this is a small enough simulation that doesn't particularly hurt anything too much, but on bigger simulations, that can be prohibitive in terms of time. So you can see this gradient walk back and forth there. So those are kind of the high points. Again, conjugate heat transfer can be very complex. You can get as complex as you want with the flow field. So this is a fairly basic example. I'm going to briefly do a sort of related type of model, but I'm not going to explain all the steps. So I'm just going to save this really briefly as just put this on the desktop. Trying to get heat transfer. 2D cylinder. Okay. Ease of use, I'm just going to nuke everything here and start again, sort of, or try and nuke everything here. Doesn't really want to let me. We can leave the domains in place because those are fine. Delete the error, delete that. I'll also delete the reports and all, or okay, I guess I gotta delete all the plot first. Bear with me a second here. Residuals. Delete. Monitors. Delete. There we go. And did I already delete my scenes? I don't believe so. Okay. Okay. We can also delete, we should be able to delete all this geometry. There we go. Okay. So we're going to do a couple of things here. Actually, we're going to do this on the 3D CAD level. How about that? So this is going to be three-dimensional. It's going to be a basic-ish heatsink sort of thing. So we are going to go with the standard reference frame of Z up. So in the XZ plane, we're going to create a sketch. This is going to be a base plate. Wait, what? There we go. It's going to be on the midpoint. Yeah, what we can do here is say that this is going to be at the origin. And we are going to fix this point. So this is the center of our base plate. Okay. We're going to make this not very big. Uh, like 3 inches. So 0.75 meters. Okay, so this block is more or less going to have a whole bunch of okay, you know what? This is just going to be a block for now. And then what we'll do is we'll pattern the things that we'll use to kind of cut away. Wow, that's considered horizontal? Okay, whatever. So that means that's a vertical constraint. So how high do we want this to be? We'll just make it a basic, approximately cubic heat sink. Meters. Actually, you know what? Expose parameter. Just height. Width. Okay. We will extrude this. Extrude. This is going to be a two-way symmetric extrude. Now, if I'm not mistaken, I actually want this to be 0.075 divided by 2. Heatsink length, okay. Okay, so this is a block out of which we are going to cut out our heatsink. So let's do a sketch. Create sketch on face. I'm blanking how I show only, project sketch, hide. I'm blanking how I view normal. Uh, okay, whatever. Fine. Doesn't matter too much. Create sketch on face. Rotate this around a little bit. So what we're going to do here is we're going to create a 2-point box. Project a sketch as construction. So this is going to have a couple of things here. Apply a distance dimension. So expose parameter, heatsink, base plate thickness. Apply distance constraint. Think and thickness. Wait, why didn't it like that? Okay. Okay, so I need this line to be coincident, collinear. That, and this I need to be parallel. And then I think the rest is pretty much locked in. I shouldn't be able to really move this at all, I don't think. Yeah, okay. Okay. So what we're going to do here is we are going to pattern. If I can figure out where the tool for that is. Oh, okay. Actually, okay. So I guess I do an extrude cut through all. That's fine. And then this, I can say pattern, linear pattern. In a specified direction. So this is going to be in the positive x direction. The distance is going to be, let's see here, can I remember the format? Dollar sign. Open bracket. Okay. Yeah. Okay, we'll just say 0.01. And there'll be like 5 of them. Select bodies to pattern. Okay, so I guess what I actually need to do instead is do an extrude. And then I can cut away. There we go. Okay, now this I should be able to pattern, I believe. Or linear pattern cut is actually exactly what I want. 0.01. Number of instances like 6. The body in question in specifically is this one. And 8. Interesting. Okay, well, it's a basic heatsink. Nothing fancy, but it's there. Now I do want to edit something about this. I don't know if I can truly parameterize that super easily right now. I could figure out how to do it, but for the moment, we'll just leave that alone. And, well, actually, what we'll do is we'll just add a bazillion of these. And we will need to expose this parameter, though. Edit. Thin pitch. 3D CAD. Low. No, not quite. What we'll also do here is we will sketch here. Nothing fancy. That's construction. These have an intersection right there. Like midpoint constraint. This is going to be like the source of our heat. Expose it. Base width. And this wants to be at 0, 0. I need to fix that there. Apply fixation constraint. Okay. Do that. What we're going to do is extrude this. Base thickness. This is going to be something like 0.05, 0.02, 0.01. There we go. Yeah, it's like an integrated circuit or something. FPGA, something similar. Okay. Update. Oh, except edit. What I want to do is not have this merge. I want this to be a separate part. So we have body 1. So let me rename this heatsink. Base. Update 3D CAD. Close. Okay. So parts. Well, let's just say new geometry part. Create parts from CAD solids. This by default should be fine. Create part contacts from coincident entities. Yes, I think this should work the way I want. Let's find out. Oh, it didn't really figure it out very well. So let's see here. Scenes, new geometry scene. Now notice I made a geometry scene and the stuff is here, but it doesn't show up. That's because down here, it still says latest surface and volume, and we don't have a surface or a volume mesh anymore. So we needed to change it back to geometry, and it shows up. So now we're going to do a new shape parts block. So we're going to leave the bottom corner right where it is. So this is negative 0.01. Or you know what? Fine. 999 or 0 right there. That's fine. We're gonna go to like 0.25 meters. Probably wouldn't go taller than that actually. 0.5. And that's probably fine. And so we're going to like negative 0.625. Yeah. So just basically knock a 0 off. Oh. There we go. So this is going to be our domain. Create. So two things here. We're going to do a subtract, new Boolean subtract operation. We're going to cut everything out of our air. This name is going to be our air. We have our base, we have our heatsink, we have our air. We need to make sure they're all touching. So new imprint operation between all three of these. Perform cat imprint as possible. Execute. We should have multiple contacts. The air is touching this base plate. This heatsink is touching the air. The heatsink is also touching the base plate, although theoretically it shouldn't be touching it everywhere, so that's a little bit curious. Okay, hold up. Oh, well, let's also split this by angle, by the way. Theoretically, I think that should be working. We'll see. In any case, this is just acting like it's aluminum. No particularly fancy stuff anywhere here as far as materials or anything like that goes. New region for each part surface, boundary mode, contacts, close, regions. So the base and the heatsink are both solids. The air is, well, air. It's fine. Interfaces. See what we got here. I'm still concerned why it thinks that. I need to figure out what's going on there. But let's create a mesh first, and then we'll get to that. So new mesh, automated mesh. This is not 2D. This is a full up 3D simulation. So we're going to mesh with a trimmed cell mesher. We do not need prism layers for this one. So the big thing here is oh wait, actually select meshers. Also, we want a surface remesher. So surface proximity, we're probably gonna want like 6 cells. The base size, we're gonna go with like 5 millimeters. Actually, we're gonna go with 2.5 millimeters base size. Target surface size, we'll go with 100. This, it can get down to much smaller if it needs to. I do not want it growing very quickly. The volume growth rate I want actually to be very slow. Maximum cell size is going to be like 400. It should not, the cells should not get very big. And then I think that should be most of it. So let's just create a mesh here and see what it looks like real fast. Oh, one important thing. Let's do this and tell it parallel. There we go. Execute. Let's try that again. Okay, so it's a little bit hard to figure out what's going on with the mesh here. So let's do a section plane straight through the middle here. And we're just going to create a new mesh scene. Oh, right. I need to change these because they think they're 2D still. They're not. These are three-dimensional. Close. Select models. This is not 2D anymore. Three-dimensional. Close. Okay. Also, I need to change the direction of gravity while I'm thinking of it. Because since we're 3D, it's in the negative Z direction, not in the negative Y direction. That's curious. Why isn't it showing me a mesh? New mesh scene. There we go. Okay, here's our mesh. That doesn't look too bad. That actually looks pretty good overall. Like, it could definitely get better, but let's see here. So if we unselect all of that and select this, this gives us a cross-sectional view. Tell you, that's fine. That's we're not being super duper picky about this. That's fine. I would like to maybe see a slightly. Well, no, this is as good as it gets. This is a 2-to-1 cell size transition, which is as good as it gets for the purposes of um, really anything that really anything with a trim cell mesh. So we're going to do another automated mesh for the air. This is also going to be trim cell. This does need a prism layer. It definitely needs a surface remesher. Base size, same 2.5 millimeters. %. Prism layer total thickness 50%. Number of prism layers, we're going to go with 12 again. Surface growth rate, I'm just going to set slow. Surface growth rate matters less for three-dimensional simulations than it does for two-dimensional. We definitely want cells, plenty of cells in between those though. So target surface size is 100 minimum, 0.25 let's say. Base size, okay, so custom controls, surface control. What I would like to do here is all of these block surfaces. These are the far fields. Yep, there we go. Are going to be coarser, potentially. So target surface size, we're going to go with 1600%. We're going to go with the minimum size. We'll leave minimum size as 12.5. I don't think anything else should be super necessary. Let's find out how much I'm going to regret this. File, save as, conjugate heat transfer, heat sink. Okay. Oh, that's... it's going fast enough. I'll let it finish the surface mesh. Stop that. So when you're doing 3D, you want to set that to parallel. Still redoing the surface mesh, but whatever. Okay. How are we doing on time? Oh, damn, this is a long one. Hour 40? Let's see. Drive parts. Yeah, that's getting real big real fast. That is a problem. automated mesh 2. So the volume growth rate, that's part of it. That needs to be very slow. Maximum cell size, 1600% is probably a bit aggressive. The base size probably needs to come down. I'm going to go 1.25. This is going to be quite a few cells. Prism layer total thickness isn't horrible. Actually pretty good. But everything just needs to get smaller. Oh, actually, hold on. There's one more thing. I just want to disable, just straight up get rid of prism layers on all of these perimeter surfaces. There we go. That looks significantly better. Maybe not great. Let me go ahead and just turn the maximum cell size down by a factor of 2, and we'll try that. Uh, Perfect. So that looks reasonable-ish. So here's what we're going to try and do here. We're just going to more or less say this base plate is generating some amount of heat. It is a total heat source. We know the chip is generating, I don't know, let's say 25 watts of power. Let's go ahead and just see if we can get... Oh, we need to set the air boundary conditions. This is just going to be straight natural convection for the moment. Which one of these is the base? That's the base. Okay. So I really should have named these. I didn't, but we'll work around it. So we'll do a couple different modes. One where this is kind of a wind tunnel, kind of where it's just open. So for now, it's just open. Let's make sure our interfaces are right. We do have 3 interfaces. So telling it initialize basically says, hey, go check where are these things actually touching. So the air is touching the top heatsink there. That is correct. The base is or they're touching each other there. And yeah, those are the 3 interfaces. So we should be okay. Am I forgetting anything? I don't think so. Oh, I should probably just straight up clear the solution before this decides to break on me in horrendous ways. Let's do a new scalar scene of temperature on our derived part, on our cross-sectional plane. And go ahead and display the mesh. There we go. Oh, we need to ask it for temp. There we go. Yeah, this is going to run a lot slower. But we're getting heat is going from the first solid into the second solid. We can see it's working its way up these fins. Notice the edges of the chips are, according to this, it thinks it's the hottest. Realistically, the heat would probably be concentrated in the center of the chip, so you wouldn't get these hot spots as pronounced in the perimeter. But nonetheless. So this will be like kind of watching paint dry. But this is a truly three-dimensional simulation. So we have little tiny, you can kind of see them, like boundary layers. Actually, you can definitely see it here. Boundary layer inside of, in between the fins. The heat's moving up in between the fin, and eventually we should really have some kind of delta T sort of thing as this figures out what's going on here. This is just pure natural convection. And we can verify just for a second that this is truly three-dimensional by creating a new, assuming I stop the simulation for a moment, a new derived section plane, and we will make it that way instead for this one. And we will add it to our existing scalar displayer. We can see that this has two directions. Very definitively. We can actually see what the thermal profile looks like inside the air gap in between some of these fins by kind of looking at this profile here. So this will take a while to fully develop. And I'm not going to wait that long for this one. I mean, I can run it in the background, but you guys don't need to watch it. But this is a more advanced application where it's like, we want to know how this heat sink cools down this chip. And this is a full three-dimensional conjugate heat transfer model. I forget how many cells this wound up having. Let's see here. This has cells. 2.3 million cells. Just a few. Just a few. So this would take a little while to figure out. And I'd probably need to run this for several thousand iterations. So it would take a couple of hours. But at this point, we're actually able to start to see a serious mismatch in the temperature in the fin versus the air. There's a noticeable gradient here, right? The air is at a different temperature than the fin as buoyancy effects start to take over and let the air rise out of those fins. So principally air is coming in through the side, getting heated and rising out through the middle here. And you can see that by this kind of spire shape of the air temperature as we're graphing it here. And this could be used for different fin thicknesses, horizontal fin, what have you. This could be used for all kinds of different stuff. But I'm going to go ahead and stop this here. The first part was kind of an actual walkthrough. It's like, the thing that matters is you have to have different regions. Solids, fluids, and you have to have contacts and interfaces between them. They have to know that they talk to each other. You have to have different physics continua for solids and fluids. If you have different types of solids, you need one for each type of solid. If you have different types of fluids, you need one for each different type of fluid. Unless they're mixing, in which case it gets more complicated. The things you want to measure, perhaps, that you wouldn't think of before. It's like you might have thought of measuring temperature before, but you also want to measure things like heat transfer coefficient. What is the maximum and minimum internal temperature? You want to look at what is the temperature of the solid in space. What does the temperature field inside of the solid look like? And things like that. And like as an example here, let me just pull up a scalar scene. Let me stop this iterating so it doesn't completely try and kill my computer. Let's look at a scalar scene on starters. We're going to look at not the surface of our block. We just want to look at our heatsink. We can turn off that outline. We really don't need it. But we are going to want, And the mesh seam probably doesn't matter. Let's say heat transfer coefficient. Well, this thinks it's pretty gosh darn consistent for the most part. The outside, it gets a little bit squirrely. But it thinks it's largely... Actually, this range doesn't tell us anything because there's some visual glitchiness going on here in like corners and tiny things. So this is a case where we probably want to truncate this range. Like, I know it's not that low. I know it's not that high. So let's go ahead and go with like negative 20 to 20. And well, that's definitely still peculiar. It's doing something weird with these calculations. So I think that gets down to what type of heat transfer coefficient did we ask? So let's see what others. Let's see here. Local heat transfer coefficient. Well, that's not stupendously helpful either. Okay, there's a couple cells in the corners where this one's a little bit confused, but specified Y plus heat transfer coefficient more or less means look at the temperature a relatively small distance away from the surface and use that as your reference when you're looking at your delta T values. So realistically, this is probably just not very well converged. It's nowhere near converged, so it looks weird. Here's part of what's going on here. I'm trying to get results off a simulation that's nowhere near done, and this is what I get. But you might want to look at what does heat transfer coefficient look like on the surface. Let's see here. Heat transfer coefficient. Or you can just look at let's see here. Boundary heat flux. Actually, hold on a second. Let me check something here. Letting this run out some more might sort of figure out what's going on a little bit, but this is probably going to take a long while to convert, so I'm not going to belabor the point too much. But you can look at the very same things in 3 dimensions as you would look at in 2. You can look at how does heat transfer coefficient, temperature, heat flux, all these things, how do they vary with position over the body? Like if we just look at temperature, for example, we get this, right? So theoretically, if the answer we were looking for, and if this were fully converged, it's not, we would say that probably the bulk temperature of this chip gets to something like 348 Kelvin, somewhere in that neighborhood. So it gets to about 75 C is where this is currently getting, give or take. Maybe that's good, maybe that's not, but if this were a hypothetical actual engineering problem, that would be the current outcome, assuming this were fully converged. Again, it's not. So, to be clear, it is very, very not fully converged. Also, the other thing is, if you force any amount of flow around this thing, that is going to pretty vastly change the scenario. So, if I attempt to... Nope, not that one. Sure, if I make these walls for a second here, and make this one a velocity inlet, we're just going to run flow at like, 2.5 meters per second through here, and this might be able to figure out what's going on here. So now note that this should mean that one side of this is going to cool down and the other side is going to heat up. Because the air is coming from the left to the right, it's hitting this face broadside, and we're getting a temperature rise on the leeward fins. You can see the chip is cooling down, all that other stuff. So let's actually flip this a little bit. So that needs to be a wall. Oh. Hopefully that's a recoverable error. I should not have changed that while that was iterating, to be clear. Let's make this a velocity inlet. Also 2.5. The top surface we want to be a wall. So this is effectively like a closed case or a tunnel of some kind. We should see this side of the chip cool down quite a lot. The opposite side will heat up some, but this in general should cool down a lot as air is allowed to move through these fins. And this side, the left as shown currently, should get quite cold as the flow moves from the left to the right, and the temperature will rise through these fins. And that is indeed more or less what we can see happening here. Again, it'll take quite a while to actually converge and get there, but that's what we're currently observing. So I will actually leave it there now. But hopefully that's informative for folks, and we can address questions, comments, concerns in the class. And I'll post some geometry that you can use as the test article for your 2D simulations. You won't need to do a 3D simulation.